we aim to achieve high-quality results with low computation costs for neural fields. Inspired by wavelets, we propose to perform spatial and frequency-wise decomposition jointly. Specifically, we segment the frequency domain into several bands. For each band, we decompose the spatial domain into smaller cells. For instance, we segment the space into 2 smaller cells for the bottom band. For better compactness, low-frequency bands are analyzed over long spans of space. Correspondingly, high-frequency bands are analyzed over short spans of space. Previous methods provide suboptimal performance and introduces much more errors. Additionally, our method can achieve improved quality with smaller network size for high-resolution image fitting, comparable reconstruction results for 3D shape fitting, and novel view synthesis results with smaller network. In details, neural fields takes the position of a query point as input and is learned to estimate the target signal value such as the density and RGB colors for radiance field and sign distance field for geometry modeling. To synthesize high-quality results with fast training speed, the state-of-the-art methods propose to decompose the input coordinates into smaller cells. Despite their empirical success in result quality and fast training speed, they do not take frequency into account. This prevents them from achieving a compact neural network and cannot synthesize high-frequency details with introduced artifacts. Here we compute the error maps for the reconstructed images to highlight the performances of each baseline. To achieve a fair comparison, we adjust the parameter numbers of all methods to a comparable level. Take the portrait of Einstein, for example. As state-of-the-art, InstantNGP uses hash grids to divide coordinate space into local regions and each time only extract a short learnable code to speed up training. In parallel, the frequency transformation-based methods like Siren operate in the frequency domain and have no concept of spatial information. Inspired by wavelet transformation, we jointly analyze the space and frequency domains in an adaptive manner. The low-frequency signals are modulated by coarse grids while the high-frequency signals are modulated by fine grids accordingly. Here are the visualizations for the error maps of all methods. Existing methods cannot present faithful reconstructions and introduce significant errors into the results, especially near the sharp regions. In contrast, our method output results with almost zero errors. Additionally, our adaptive space frequency learning also yields faster convergence speed. For the first 5,000 iterations, we can achieve better results with more than 5 PSNR than existing methods. We implement the following architecture to reflect the aforementioned motivation. First, like existing methods, we implement the spatial decomposition with hash grids. We perform the spatial decompositions in a multi-scale manner for more effective scale modeling. Then we explicitly associate the frequency biases with hash grid sizes via the Fourier feature network. Specifically, we apply small frequency transformation coefficients for coarse grids and large coefficients for fine grids, which is implemented by adjusting the initialization variance of Fourier feature network. We next apply a set of sign-activated fully connected layers for frequency decompositions. To connect the frequency domain with space domain, we use the frequency encoded grid features to modulate the sign-activated features from fully connected layers. Lastly, like wavelets, we compose the features from all levels to output final signal values. We evaluate our method with 3 different tasks. The first one is 2D image fitting. Qualitatively, our method can reproduce realistic local structures of buildings as well as the words on the billboard. In comparison, InstantNGP produces more visible artifacts for the far regions while other baselines distort the highlighted billboard fonts and building structures. Here we also show the quantitative results for the reconstruction of high-resolution images. With similar learnable parameters, our method can get the best result quality. For example, our method can achieve more than 3 dB in PSNR compared to Siren even with smaller network size. And compared to InstantNGP, we can achieve improved PSNR, SSIM, and LPIP scores with less than 1/3 learnable parameters. Moreover, for the Einstein image, our method can synthesize best results with faster convergence. Specifically, for the first 5,000 iterations, our method can outperform baselines with greater than 5 dB in PSNR. For 3D shape fitting, our method can achieve on-par geometry detail reconstruction with about only 3% of parameters. This can be also reflected by reporting the score comparisons. We can achieve similar scores in F-score, IOU, and chamfer distance. We also evaluate in the NERF settings. Compared to the original NERF, we reduce the iteration number to its 10% and thus have faster training speed. For instant NGP, we can achieve similar PSNR and SSIM scores with less parameters. In summary, we propose a novel framework to decompose the target signals in both space and frequency domains adaptively. With this wavelet-inspired idea, our method can achieve better trade-off between result quality and network compactness in the tasks of 2D image fitting, 3D shape reconstruction, and novel view synthesis. For more details on our implementations and other technical contents, please refer to our released codes and project webpage.